So now we'll be moving into a whole new arena. We'll be looking at wireless technologies. This is a new target on the CISSP exam, and there's a great deal of technology to learn and understand relative to securing your wireless networks. We'll also look at instant messaging, another huge vulnerability in your information systems. And then we'll look at some specific attacks on these technologies. The first component that you'll probably acquire for your wireless system would be the access point. The access point is the mediator for the wireless arena or cell. The cell, the definition of a cell, is the wireless access point and all the nodes that are associated to that access point. These wireless technologies are specified by IEEE standards 802.11. That's wireless. There are several others that have been added to this, but the basic wireless standards are based on IEEE's 802.11 standards. Wireless technologies are using spread spectrum technology to provide error-free transmission from sender to receiver. They use access points and as wireless devices. These would be the nodes that are associating with those wireless access points. Some things we'll be looking at are the authentication process, that is, who are you? Okay, I believe you are who you say you are. The authorization process, that says, now that I know who you are you allowed to be touching that? And last one is the association process. Once you are authenticated and I recognize that you are authorized, I will let you be associated to the access point. Association is required before you can transmit your very first data frame. So before you can start using the wireless network, you have to authenticate and be authorized to use the wireless network. We'll look at the wireless protocol stack and some security issues related to the wireless protocol stack and many common attacks on the wireless networks. We'll then also look at how you can defend yourself against these attacks. First, to put it in perspective, what are we talking about here? We're talking about radio frequency transmissions. These are electromagnetic waves that are filling the airspace. They are approximately 4 inches in length for a 2.4 gigahertz system, about 2.5 inches in length for a 5 gigahertz system. These are the two frequency ranges that are allocated for wireless network use. 2.4 gigahertz and 5 gigahertz are the two ranges. Now these are identified in the graphic with the green band and they are about the size of a standard computer mouse. What we see though is that these radio frequencies, these sine waves, can range from the length of a football field or longer, maybe even miles in length, down to so small they are even smaller than the size of the nucleus of an atom. So it's a huge, huge spectrum on the length of these radio frequency waves. We're operating in the range of about 4 inches long for a 2.4 gigahertz system, about 2.5 inches long for a 5 gigahertz system. As I indicated, IEEE wrote a series of standards based on 802.11 that are used to define wireless networking for data communications on your networks. So 802.11 was the first wireless spec. The spec included a speed of about 2 megabits per second maximum. It included 3 different transmission methodologies. The first one was infrared. Infrared really only got you about 1 megabit. And it uses photons, infrared, not visible, photons at 2.4 gigahertz. The second methodology was direct sequence spread spectrum. And the third one was frequency hopping spread spectrum. So this got you up to about 2 megabits per second and operated in the 2.4 gigahertz frequency range. Again, about 4 inches in length in airspace. The second spec that came out was an enhancement or a modification to 802.11. It was called 802.11b. It increased the data rates to 11 megabits per second. Still operated in the 2.4 gigahertz range. Still tolerated all three, infrared, direct sequence, and frequency hopping spread spectrum. And again, increased the data rates to about 11 megabits. The next specification that came out was 802.11a. Now 802.11a was introduced because it operates at 5 gigahertz frequency range. See, the 2.4 gigahertz frequency range is commonly used for industrial, scientific, and medical purposes. And there's a lot of business, a lot of devices operating in the 2.4 to 2.5 gigahertz range. So that meant there was a lot of interference with your wireless networks. So to step away from all that noise, if you will, interference in our wireless networks, they introduced 802.11a. 802.11a operates at 5 gigahertz, which is another section of industrial, scientific, and medical use, but it also includes a range called the Unlicensed National Information Interchange, or the UNI bands. So it gives me a broader spectral range. Here I go from 5 gigahertz to 6 gigahertz, a whole gigahertz of range that I can introduce my information flow on, versus the 2.4 to 2.5 gigahertz. This is only 0.1 gigahertz frequency range. So I have more space, I have fewer devices up there to interfere with, and they also introduced another whole new technology with 802.11a, and that is something called orthogonal frequency division multiplexing, OFDM. Now, OFDM is not a spread spectrum technology, even though it very often gets lumped in that same category. We'll be talking more about OFDM in a few minutes, but you see the data rates here run up to 54 megabits per second. There are also some proprietary technologies that take OFDM up over 100 megabits. So we'll be discussing those in a little while. Now, shortly after 802.11a came out with the introduction of OFDM, the guys in the 2.4 gigahertz range said, hey, if they can do OFDM, we can do OFDM also. And so now they added OFDM to the 2.4 gigahertz range to get the data rates up to 54 megabits. And they operate now with 802.11g at 2.4 gigahertz and 54 megabits. So that's the historical perspective of how we got to where we are with 802.11 and our transmission mechanisms on the wireless networks. Now, 802.11 specified security for the wireless network in a protocol called WEP, Wired Equivalent Privacy. Unfortunately, they had wireless guys, wireless engineers, defining security components. They should have had security guys defining the security components for 802.11. WEP was riddled with flaws. There is vulnerability upon vulnerability in WEP. And once we realized all the vulnerabilities in WEP, they knew they had to fix it. So they introduced another spec, 802.11i. 802.11i is the enhanced security to replace WEP that was introduced in 802.11. It includes two protocols called WPA and WPA2. That's Wi-Fi Protected Access. And the second version of Wi-Fi Protected Access. That's WPA and WPA2. These are solid, secure security for the wireless network, and they solve all the problems that WEP had. If you're running a wireless network, you need to be running 802.11i. We'll be talking more about this in a few minutes. Another spec in the wireless arena now steps away from 802.11. It's 802.15. This is for personal area networks. This specifies networks that range in a wireless fashion up to about 10 meters. That's about 33 feet. This is Bluetooth, Zigbee, infrared. They all live in the 802.15 specification. So that's a personal area network up to about 10 meters. And then 802.16 is the other end of the spectrum there. That is wireless metropolitan area network. So this is the last mile, the last couple miles specified by 802.16. This is the arena where WiMAX lives. We also are seeing another new label in this arena called wireless regional area networks. And again, this is simply increasing the distance that our clients can be away from the access points in the wireless network and still provide good, solid connectivity. One of the significant problems we face in wireless networking is the problem of interference. And that's why we use frequency hopping spread spectrum, direct sequence spread spectrum, and orthogonal frequency division multiplexing, OFDM. The problem is if there is some sort of noise on a particular frequency, and that's the frequency I'm trying to use to transmit, I may not get any data transmitted through because the interference destroys the integrity of my information. When we introduce something like frequency hopping spread spectrum, what we do is we actually take a frequency range, and every few milliseconds I jump to a different frequency within that range. In other words, if I have interference at this frequency, I may only land on that frequency twice a second for just a small amount of time, a few milliseconds perhaps. So I might take a hit due to the interference destroying my data for that brief period of time, but because I have spread my signal out over such a large band frequency range, most of my data gets through, and the data that gets corrupted, I'll retransmit that as needed. This is through error detection and correction technologies that go along with the frequency hopping spread spectrum. Interestingly, frequency hopping spread spectrum was patented by the actress Hedy Lamour and her pianist during World War II, as they discovered that the Germans were jamming our radio frequency signals that were steering our torpedoes. What they discovered was if we change the frequency to a different frequency, the Germans can only jam one signal while I get enough data through that I can steer my torpedo to hit their ship. So this was really what was the impetus for the creation of frequency hopping spread spectrum. Again, I bounce that frequency around through the range of 2.4 to 2.5 gigahertz. And again, if I suffer narrowband interference, it doesn't matter. I'll lose a little bit of data, but most of my data gets through, and I'll recover the data that gets destroyed due to the interference. The next spread spectrum technology is called direct sequence spread spectrum. This takes a very large frequency range and transmits the same data over this large bandwidth, so that if there is narrowband frequency, it doesn't matter. The receiver can hear the shoulders, if you will, to above and below the point of interference. So I still have a single channel of data transmission, still a single data stream, much like a serial cable, but because the frequency range is so broad, narrowband interference doesn't bother me too much. Yes, I lose a little information there, but it doesn't matter because my receivers can hear the frequency above and below where the point of interference is, and I can still get a great deal of information through. This is called direct sequence spread spectrum. The last one, OFDM, really isn't a spread spectrum technology. Basically what it does is it takes 48 discrete data signals. These are like 48 wires, whereas frequency hopping and direct sequence use approximately a single channel for communications. OFDM uses 48 different channels for communication, and as a result I can send a lot of data through. This is how we afford these greater data rates with OFDM. So again, orthogonal frequency division multiplexing is not a true spread spectrum. Even though it uses a large spectral range, it uses 48 discrete channels for data communications. By the way, there are 2 channels on either side, a total of 4 channels for control for error detection and correction as well. Here we see some diagrams trying to demonstrate the difference between direct sequence, frequency hopping spread spectrums. In direct sequence spread spectrum, I have a broad range of frequency that I'm transmitting, all a single data stream. So one channel, even though it's a broad frequency range, one data stream. And you see we have one data frequency at 2.412 gigahertz, another one at 2.437, and a third one at 2.462 gigahertz. Even though the access points tout 11 channels to choose from here in the United States, there's really only 3 that anyone should ever use. These are the 3 frequencies, and they typically are called channel 1, channel 6, and channel 11. If you use any channels other than 1, 6, or 11, you're probably making a mistake, because they will then begin to overlap with the standard channels of 1, 6, and 11. So direct sequence uses a very broad spectral range, but still only one data stream. It's like having one wire to send data down the wire. Frequency hopping spread spectrum is a single data stream, but the signal bounces between different frequencies very rapidly. I hop from one frequency to another, and this is to avoid being on any frequency that has interference for any length of time. So even though that interference will destroy the data on that one frequency, it doesn't matter because I've got all these other frequencies, about 75 other frequencies that I can bounce around to where I don't suffer that interference. Again, these two spread spectrum technologies only transmit a single data stream at a time.